Hello and welcome to Lecture 30 on the final part of our Taylor series lectures. So in this lecture, the goal is just to do some more practice with Taylor and Maclaurin series. So let's take a look at this first example. We're going to find the Maclaurin series for ln of 1 plus x, and we're also going to find the radius of convergence for this Maclaurin series. So first thing we're going to do is we're going to make an observation. So observe that if you take the derivative of ln of 1 plus x, what is that equal to? Well, the rule for log is you do 1 over whatever's inside the log, so 1 plus x. And the derivative of the inside is just 1, so there's nothing that needs to be multiplied due to the chain rule. So we just have this. And then if you recall back to our strategies for finding power series, we can very easily manipulate this using the geometric series formula. So we're going to rewrite this as 1 over 1 minus a minus x. So those are equivalent. And then from here, I can use the geometric series formula. So this is equal to summation n equals 0 to infinity. And then whatever you have here in parentheses, if you have 1 divided by 1 minus something, this something is going to be plugged in. So you have negative x to the nth power. And this is the same thing as having summation n equals 0 to infinity. And instead of this negative sign being here, I'm going to bring it out front here. So I have negative 1 to the n, x to the n. And this will be valid for when the absolute value of x is less than 1. So this is the radius of convergence for this series right here. So r would be 1. OK, so now that we have this, what I'd really like to do is figure out, well, what is the series for ln of 1 plus x? So to go from here to ln of x, you would have to integrate this. Because if I differentiate and get this, then that would imply that the integral of this gets me back to where I started. So I'm going to integrate the summation n equals 0 to infinity, negative 1 to the n, x to the n, dx. And I can do this term-by-term integration as long as I specify that I'm on this interval for x. So from negative 1 to 1, I am certainly OK to do that. So I'm going to integrate this to get back to ln of 1 plus x. So doing my term-by-term integration from the other lecture videos, you're really just focusing on this x component right here. So how do I go backwards from x to the n? Well, what I do is, first let me rewrite everything else. So this is the summation n equals 0 to infinity. Negative 1 to the n is a constant with respect to x. And it's this part I'm focusing on, which is x to the n plus 1 divided by n plus 1. And I've integrated. And this is an indefinite integral, so I'm going to need plus c right here. So what I have now is a general antiderivative for this series. It'd be helpful if I could figure out what c is. So if this is supposed to be equal to ln of 1 plus x, because remember the integral of this we get us back to ln of 1 plus x, let's plug in an x value inside our interval of convergence. So if x equals 0, and we're going to plug it into both sides of this equation. So if you plug it in on the right, if x equals 0, you get ln of 1, which is 0. And if you plug in 0 for x on the left side over here, I get 0 to any power here is just going to make this whole sum 0 plus 0 plus 0. So I get 0 plus c for the left side. So this just tells me that c is supposed to be 0. So now I can really write that ln of 1 plus x, which is what I was looking for. I was trying to get the series for that. ln of 1 plus x is summation, I'm just copying what I got right here, which is n equals 0 to infinity, negative 1 to the n, x to the n plus 1 over n plus 1. So this is the Maclaurin series for this, which means the center is at 0. So Maclaurin series just means that the center is at 0. And here is my series representation for that. Now, one thing I could do, just to remind you of other algebra things you can do, is that if I wanted to make sure this was x to the n, if I wanted it to look like that, I very well could do that. So I could decrease all of these n's by 1. So I could say I have negative 1 to the n minus 1, x to the n, and n. So I've decreased all of my n's by 1. And how that would shift for the indexes, I would increase by 1 here. So I'm just reminding you that that's something you can do. You can shift the index if you like, if you prefer to have your series look like this, an x to the n, instead of having x to the n plus 1. So this is our Maclaurin series. And the radius of convergence, we get that from this right here. The radius is going to be 1. OK? So that's that example. Now what I'm going to do is I'm going to use this series representation to approximate the integral of ln of 1 plus x dx to an accuracy of 0.001, which is 1 over 1,000. That's 1/1000th. So let's take a look at that. So we know that this integral right here, 0 to 0.5, ln of 1 plus x dx, well, we can replace this with the series representation that we just found. So this is the integral from 0 to 0.5. And I'm going to fill in what I have for my series. So this is n equals 1 to infinity. I'm just filling in my answer from over there of what ln of 1 plus x is. Negative 1 to the n minus 1, x to the n divided by n, and then dx. So we have this. Now I'd like to go ahead and integrate this term by term. I can do that as long as I'm within the interval of convergence. This, recall, is at least some of my interval of convergence, right? I could have to include an endpoint or not. I didn't check, but it's not going to matter. From 0 to 0.5, we're certainly within the interval of convergence, OK? So don't worry about the endpoints for this particularly. So I'm going to plug in these as my upper and lower bounds after I integrate this term by term, which I'm OK to do on this interval of convergence. So let's keep going. So if I integrate this, just like I did over there, I'm just going to focus on this x portion. So integrating, I get the summation n equals 1 to infinity, negative 1 to the n minus 1 over n. That's a constant with respect to x. And then here, I have x to the n plus 1 over n plus 1. So that was me using the power rule in reverse here. And then we have a definite integral this time, so I don't need plus c. I just need to evaluate this from 0.5 and 0, just like that. So that's where we are so far. So now what I'd like to do is make sure my answer is going to be within this level of accuracy, the 1 over 1,000. So let me talk through that. So we need the first term such that we need to find the first term of this series such that the absolute value of a sub n is less than 1 over 1,000. And remember, what we're doing for this is called the alternating series error estimate. So we had this theorem that lets you know the maximum amount that your series can be off by estimating using the first few terms. So I'd like to first call this a sub n and just figure out where is the first term where I'm strictly less than 1 over 1,000. Well, it turns out that if I look at n equals 4, I'm just going to do a couple of them to show you what happens. So if n equals 4, then I would look at the absolute value of the fourth term. And what is that equal to? Well, I would plug in my 0.5 for x. So here, taking the absolute value, this negative 1 to the n minus 1 is disregarded, and I would get 1/2. That's my 0.5 right here. I get 1/2 to the 5th power, because I'm plugging in 4, divided by, and I plug in a 4 and a 5. And remember, because I'm taking the absolute value, I'm just ignoring the negative 1 to the n part. But I've plugged in everything else here. Well, what is this? This is 1 over 32. And then also multiplied on the bottom is 20. So here, this is actually greater than 1 over 1,000. If you multiply these together, it's not quite large enough for this. So we have not yet found the first term such that we're less than 1 over 1,000. That's what we're searching for to use the alternating series estimation theorem. So now I'm going to do 5. So if you look at the 5th term, the absolute value of the 5th term, again, I'd be plugging this 0.5 here. So I would have 1/2, and 5 for n would mean this is 6. And then in the denominator, I have 5 times 6, which this gives me 1 over 64 times 30. And if you work that out, this is the first value of n where we are strictly less than the 1 over 1,000 that we need for our estimation. So what this tells us is this is the first term where that occurred. So therefore, we require the first four terms. So with the first 4 terms, we can get this estimate accurate enough to be within this accuracy right here. So we use the first 4 terms, and then the next term that you get tells you how far off your estimation is. So we need the first 4. So that means that I'm going to take this right here, and I'm going to use the first 4 terms. So what do the first 4 terms look like? Well, this means that this is approximately going to be, and I'll plug in the first one, which if I plug in 1 for n, I get 0.5. And if I plug in 1 for n here, I get squared over 2. So this was n equals 1. And if I keep going to the second term, I would get minus, because this is alternating, it'd be 0.5 to the 3rd over 2 times 3. Moving along to my third term, it alternates back to plus, and I get 0.5 to the 4th over 3 times 4. And then finally, to finish my estimate, it would go back to negative, and I'd have 0.5 to the 5th over, and then this would be 4 times 5. So this is what happens when I use the first 4 terms and I plug in 0.5. So using these first 4 terms, this would be an estimate that is within 1/1000th of the actual true answer for this integral right here. OK, so I hope that helped, giving you another example of estimating an integral using series. When we come back, we're going to be looking at a couple more example problems of Taylor series. So I'll see you for that in just a moment. Welcome back. Let's look at these final 2 examples of Taylor series. So before I do these, I want to remind you of the general formula for finding a Taylor series. So let me write that at the top for you for your notes. So the Taylor series formula is a function f of x is equal to summation n equals 0 to infinity of the nth derivative of f at a, where a is the center of the series, divided by n factorial times x minus a to the n. So we call a the center, like I just said, and this expands, if you do the first few terms of this, this expands into the function at a. So if you plug in n equals 0, you get f of a. If you plug in n equals 1, you get f prime of a over 1 factorial, which is just 1, times x minus a to the first power. And I'll do one more, just so you can see what's going on. So if I plug in n equals 2, you would get the second derivative at a over 2 factorial, and then times x minus a squared. And this pattern continues forever. So sometimes I'll ask you to get a Taylor polynomial, and I'll ask you to stop at a certain power of x. So it's good to know what it looks like expanded out. For both of these problems, though, I'm going to find the entire Taylor series for this one specifically. And this one is a polynomial, so it will stop at a certain point. But yeah, I'm just writing that formula out for you because you're going to need it for both of these problems. So here's the first one. We're going to find a Taylor series for this polynomial that's degree 3 at a equals -2. So I know that after a while, if I take enough derivatives, for this polynomial, the derivative will go to 0. I know that ahead of time. If you take a couple derivatives, we decrease it to the second power, first power, and then finally it reduces to 0. So for something like this, I'm just going to kind of write out every piece that I need here. So I know that the original function is x minus x cubed. And I'm going to begin by taking many derivatives. So the first derivative is 1 minus 2x squared. The second derivative is going to be -6x. The third derivative is going to be -6. And then here's what I was talking about. Once we've reached the fourth derivative, at the fourth derivative and anything beyond the fourth derivative, all the derivatives will be 0. So what's going to happen is once you get to the fourth term in this expansion, it's 0 plus 0 plus 0. So you kind of lose everything else, and it's really just these are the stars of the Taylor series for this, and that's all you need. What else do I need for the Taylor series? I have to evaluate them all at a. That's an important piece of the formula. You plug in a for all of these derivatives. So next to these, I'm going to use my a, the center, which is -2. And I'm going to plug in -2 into all of these. And we're just going to hope I don't make an arithmetic mistake. So for the first one, if you plug in -2, you're going to get 6. If you plug -2 into the first derivative, you get -11. If you plug in -2 into the second derivative, you get 12. And if you plug in -2 into the third derivative, you're going to get -6. So these are the numbers that I got when I evaluate the first, second, and third derivative at a. They're going to be important in the formula here. So now I'm going to go ahead and write out my formula. So the Taylor series is, so this is f of x is, my first term is going to be f of a. So f of a was 6. Moving right along, so I move to the next one. F prime of a is right here. It's -11. And then I have to do times x minus, and then it's a -2 for my center. So actually that's +2 to the first power. Next, I need to do the second derivative at a, which is 12. And then you divide it by 2 factorial. And then it's x minus, or well, minus a minus, so +2. And now it's squared. And notice I'm going to need one more term. So let's just follow the pattern. I need one more term here. So for the third derivative, I have minus 6. You divide it by 3 factorial if you're following the pattern. And then this is x plus 2 cubed. There's a very minor simplification that you would want to do here. So maybe you could do 6 minus, I'm not even going to distribute that, but 2 factorial is 2. So this would be 6 right here. I would leave it in this nice form where you have these x plus 2 factors. And then 3 factorial is 6. So this will just be minus 1 of these. And there you have it. So the point of this is, if you were to take the time and FOIL this all out and simplify, this would be the original that you started with. If you really wanted to be meticulous and check your work, or you could just plug this into a calculator. So we represented this function as a function centered at 2, or negative 2, sorry, instead. But this is equivalent to this. That's the point. We've just changed the form of what this looks like. All right, so now let's do it for something a little more complicated. So in this case, you're going to see that as you take derivatives, it's not going to go to 0. This is not a polynomial. It has a negative for its exponent. So to find a general Taylor series with something like this, where as you take derivatives, the derivative does not go to 0, you're going to need to be careful, and you're going to need to find patterns in order to figure out what the Taylor series is going to be. So let's take a look. We have f of x. Well, that's x to the negative 2 power. OK, so now my first derivative, if I bring the negative 2 in front when I take the derivative, it's going to be negative 1 and then 2x to the negative 3 power. So what I'm doing, and what I advise you to do, is if you're taking derivatives and you notice that you're going to be bringing down negative numbers, keep track of how many negative 1s come in front. Because the derivative means I bring the negative 2 in front, right? So I'm just going to split that up into negative 1 times 2. Let's continue. The second derivative is I'm going to bring a negative 3 in front. So I have another negative I've brought in front. So that's negative 1 squared. And then this one is 3 times 2. And this is x to the negative 4. You need to very carefully keep track of things. I really advise you not to simplify, because you need all the help you can get to identify the pattern that's happening. Because what you're going to have to do is you want to find a formula for f, the nth derivative of f at a. You're going to try to figure out what that is, because you need to plug that into the formula. Let's do one more derivative and then see if we can identify the pattern. So the next derivative gives us another negative. So this is negative 1 cubed. And then I get 4 times 3 times 2 x to the negative 5. So at this stage, I should probably start asking myself, OK, what is the nth derivative at x? Let's pretend now that I took n of these. So what's the pattern? Look to some previous ones to get an idea. Well, I want to start with the power of x. When I hadn't taken any derivatives at all, so you could count that as the 0th derivative, I was at a negative 2. The first derivative, I'm at negative 3. The second derivative, I'm at negative 4. So what you should notice is, if you take the derivative number you're on, it's separated by 2 with this number right here, right? First derivative 1 and 3 are separated by 2. Second derivative and 4 are separated by 2. So nth derivative means that this number should be n plus 2, right? If this is 3, this one's 5. If this is n, this is n plus 2. And what do I need to tack onto that? Just a negative sign in front, because all of them have a negative sign in front. OK. Let's take a look at the power of negative 1 that we'd be keeping track of. So for the first derivative, I have a power of 1. For the second derivative, my negative 1 is to the second power. So it looks like these match exactly for the third derivative, I have negative 1 to the third power. So for the nth derivative, it's negative 1 to the nth power. And then finally, let's look at this. So here I have 2. This is 3 times 2. This is 4 times 3 times 2. So what's going on here is we have some sort of factorial thing going on. Well, on the third derivative, you have 4 factorial. On the second derivative, you have 3 factorial. So they're off by 1. So on the nth derivative, you'd have n plus 1 factorial. So that's the pattern. This is probably the hard part of doing the Taylor series, is you have to do enough of these and keep track of enough to be able to find the general pattern. So this is my general nth derivative, and now I can use the Taylor series formula. So the Taylor series is equal to, I'm just rewriting the formula at this point. It's n equals 0 to infinity. F of n at the center, the nth derivative at a, n factorial, and then x minus a to the n. All right, but now I'm ready to fill this in. What is the nth derivative? And the center this time is 1. What is the nth derivative at 1? Let's plug it in. 1 is an x value here, so this is negative 1 to the n plus 1 factorial. If you plug in 1, 1 to any power is just 1. So the nth derivative at 1 is going to be summation n equals 0 to infinity. This a right here is 1. So I found out what f, the nth derivative of f at 1 is. It's going to be plugged in right here. And that is negative 1 to the n plus 1 factorial. And I'm going to continue using the formula now. So I found this general term. I'm going to divide by n factorial. And then I get x minus, and a is 1. The center is 1 to the n. Can you simplify? You sure can. We did lots of practice problems with the ratio test, right? So we know that n factorial, or n plus 1 factorial, sorry, n plus 1 factorial, all that is n plus 1 times n factorial. It's n plus 1 and then the rest of the factors multiplied. So what happens is these two cross out, but you still have an n plus 1 in the numerator. So you just have that one remaining. And this is x minus 1 to the n. And now, am I happy with that answer? Yeah, I think I am, because this right here, this x minus 1, it's to the n. I don't really want to shift this. I think this looks fine. So this is my answer for the general Taylor series for this function right here. All right. I hope it was helpful for us to do this for another video, for us to practice just more power series and Taylor series concepts. As always, please reach out to me if you have any questions. And until next time, I'll see you in lecture 31. Have a nice day.